the Federated learning for the age. This paper introduced a new approach called HCEF, which stands for Heterogeneity-Aware Cooperative Age-Based Federated Averaging. The main goal of HCEF is to make AI training on mobile devices faster and use less energy by intelligibility adaptive each device's capability. Let me walk you through how this scheme works. First, let me provide some background on the problem this paper is addressing. Traditional federated learning has significant limitations. On the left slide, you can see it relies on a distant central cloud server. This creates high latency and presents a single point of failure. This makes it unsuitable for delay-sensitive application. On the right side, to address this, researchers developed cooperative federated learning, or can call it CFEL. Instead of one cloud server, CFEL uses multiple edge servers located at cell phone towers to coordinate training locally. Edge servers only communicate with their nearby neighbors. This solves the cloud bottleneck problem and provides better scalability and robustness. At the bottom, however, CFEL introduced a new challenge, managing the diverse and dynamic nature of edge devices, and that's the gap this paper aims to fill. The paper identified what they call the struggle problem as the main bottleneck of CFEL. In any training round, the entire system must wait for the slower devices to finish. Looking at the diagram with different devices icon, the paper highlights two types of heterogeneity. First, computation heterogeneity. Some devices have powerful CPUs and long battery life. They can be 10 times more powerful than others. When all devices are given the same fixed workload, faster devices finish quickly and then sit idly, waiting for the stragglers. Second, communication heterogeneity. Network conditions vary dramatically. Different bandwidth, different signal strength. Transmitting the full model update can be a major bottleneck for devices on slow connection. On the right side, the author used a race analogy. Fast runner have to wait for the slower person. That is a waste time and wasted energy. To address this problem, the paper proposed HCEF. HCEF is designed to maximize model accuracy while minimizing training time and energy consumption. The key innovative is this. Instead of treating all devices equally, HCEF tackles heterogeneity by dynamically adaptive to each device's capability at every communication route. Looking at the two icons below, the scheme achieves this through two mechanisms. On the right, adaptive computation, adjusting how much local training work each device performs, and on the right is adaptive communication, personalizing how much data each device transmits. By joining optimizing both mechanisms, HCF eliminated the struggle problem and made the whole system more efficient. Let me explain how these two mechanisms work in detail. On the left side, for adaptive local update frequency, the concept is instead of giving every device the same number of updates, HCF assigns each device a personalized local update probability denoted as raw. This rationale is that devices with higher computation power get a higher raw, so they perform more updates without becoming stragglers. Slower devices do less work, which prevents them from delaying the entire round. This mitigates the struggle effect and improves both time and energy efficiency. On the right side, for adaptive gradient compression, here devices don't send the full model update. HCEF uses stock K specification and assign each device a unique compression ratio denoted as delta. Devices with faster network connection can send more data. A higher delta, which improves model quality. Devices with slower connection send less data, a lower delta, avoiding communication bottlenecks. At the bottom, the key contribution here is that HCEF find the optimal balance of rho and the delta for every devices in every round. This joint optimization is what makes scheme efficient. Now, how does HCEF determine this optimal value? Looking at the equation on the left, the author formulated this as an optimization problem. The objective function is to minimizing the convergent error bound of the model. These mathematical functions capture the trade-off involved. Higher update probability, rho, increase the error but reduce the additive error. Higher compression, delta close to 1, reduce the stochastic error. Below that, optimization is subject to two constraints, time budget and energy budget. The time constraint ensures that the total estimated training time, which include mu for computing time and nu for computation time, don't exceed the budget. The energy constraint ensures that the total estimated energy consumption, which include alpha for computation energy and P for transmissive power, stay within the budget. At the bottom, the algorithm works as follows. At each round, devices report their current capability, mu and nu, and alpha. A central coordinator then solves this optimization problem to determine the optimal rho and delta for each devices. This happens dynamically, adaptive to changing condition every round. Now, look at the experimental result. The author tested HCEF on the CIFAR-10 dataset with a target accuracy of 70%. On the left, looking at the time comparison, the baseline method CF takes 4.24 times 10 to the 4 seconds, and HCEF only takes 2.22 times 10 to the power of 4 seconds. That is 1.9 times faster. On the right, for energy consumption, CEF used 7.73 kilojoules. HCEF only used 4.24 kilojoules. That is 1.8 times more energy efficient. At the bottom line, the result demonstrate that by intelligently adaptive to device heterogeneity, HCEF significantly reduced resources overhead without sacrificing model accuracy. It achieved the same accuracy level but much faster and with less energy. Let's exam- exam- let's see the performance in more detail. On the left graph, this shows test accuracy versus time. Notice that HCEF, the tail line, has the steepest curve, meaning it converges to the target accuracy fastest. The exact numbers show HCEF reaching 70% accuracy at approximately 0.22 times 10 to the power of 5 seconds, while CEF takes only 0.242 times 10 to the power of 5 seconds. On the right graph, the same pattern holds for energy consumption. HCEF reached 70% accuracy using around 4.2 kilojoules compared to the CEF 7.73 kilojoules. At the bottom, the key observation the author made is that HCEF consistently outperformed on benchmark scheme, including CEF-F, which only adapt computation, and CEF-C, which only adapt communication. This demonstrates that the joint optimization approach is critical for achieving superior performance. The author also validated the approach on more challenging dataset called Fastness. This is a naturally not IID dataset, meaning the data distribution is highly skewed across devices and is large scale than CIFAR-10. On the left graph, the results show that HCEF reached the target accuracy of 75% significantly faster than the other method. On the right graph, similarly, HCEF consumed far less energy to reach the same accuracy goal. At the bottom, the author concluded that on this natural not IID and larger scales dataset, HCEF advantage in time and energy efficient remains significant. This validates the effectiveness of their adaptive approach across different scenarios. The next experiment is particularly interesting. The author investigate how performance change with increasing data heterogeneity. At the top, the variance of dialect contraction parameter beta on CIFAR 10, a smaller beta means more non-IID data, which is more representative of real-world condition. Looking at the left graph showing a runtime, as beta decrease from 10 to 1, as data become more heterogeneous, all methods require more time. However, the performance gap between HCEF and other methods widen. In the middle annotation, the author specifically this. As data heterogeneity increase, HCEF advantage become even more pronounced. On the right graph, the same pattern appears in energy consumption. At beta equal 1, HCEF used approximately 2 kJ, while CEF used around 7 kJ. At the bottom, the paper concludes that HCEF adaptive nature make it particularly well suited for realistic statistics heterogeneous federated learning scenario. The harder the condition, the bigger HCEF advantage. The author also evaluated performance across different network configurations. At the top, they simulate various edge backhill network connectivity using random graph with different edge probability, pH. Higher pH means more connection between edge servers. On the left graph showing runtime, as pH increase from 0.2 to 1, as the network become more connected, our method improve because information can spread more efficiently. On the right graph showing energy, as the annotation indicate, HCEF consistently remain the most efficient solution across all network densities. At the bottom, the author also conclude that whether the network topology is spread or fully connected, HCEF provide the most resources efficient solution. The adaptive optimization is robust to different network configuration. The paper also examines sensitivity to aggression frequency. At the top, author analyzed the effect of the intercluster aggression period Q. Smaller Q means more frequent aggression between edge servers, which improve information sharing but increase communication overhead. On the left graph showing time, as Q increase to 2 to 10, as aggression become less frequent, training time increase for all methods, which is expected. However, HCEF maintains its efficiency advantage across all aggression frequency. On the right graph, the energy consumption show the same pattern. So that we can conclude while tuning the aggression period method, HCEF consistently outperforms other schemes. This demonstrates that adaptive optimization itself is not just hyperparameter tuning, it's the primary driver to the efficiency gain. So, let me summarize the main contribution of this paper. First, the author proposed a novel scheme, HCEF, that integrate adaptive local update and gradient compression to address system heterogeneity in cooperative federated edge learning. Second, they formulate a theoretical framework and automation problem that jointly control computation and communication while balancing accuracy against resources constraint. Third, they develop an efficient algorithm that dynamically determines optimal update frequency and compression ratio for each device, adaptive to changing conditions round by round. 4. Through extensive experiments, they demonstrate that HCEF achieves significantly shorter training time and lower energy consumption than existing method while maintaining high model accuracy, especially under challenging conditions. In conclusion, this paper presents HCEF as a practical and effective solution to the struggle problem, making federated learning more viable for real-world, resources-constrained mobile edge network. So this is the end of my presentation, and thank you, Professor.